In this video, we will explore the actual step-by-step mechanisms of major radical reactions and see how they are applied to practical synthesis. At the core of these reactions, almost every radical mechanism follows a distinct three-step framework. Initiation, where reactive radicals are first generated. Propagation, the self-sustaining heart of the reaction where products are formed, and radicals are continuously regenerated. And termination, where remaining radicals combine to bring the chain reaction to a halt. Section 1. Radical halogenation of alkanes. Now, let's dive into the step-by-step mechanisms of radical reactions, starting with the halogenation of alkanes. The reaction begins with initiation. Light or heat induces homolytic cleavage of the halogen-halogen bond, generating two highly reactive halogen radicals. Next is propagation, the self-sustaining heart of the reaction. In the first propagation step, the halogen radical abstracts a hydrogen atom from the alkane. Notice how the fishhook arrows illustrate the formation of a new HX bond, leaving an unpaired electron on the carbon to create an alkyl radical intermediate. In the second propagation step, this newly formed alkyl radical abstracts a halogen atom from another halogen molecule. This yields our final alkyl halide product and regenerates a halogen radical, which goes right back to fuel the first step. This cycle repeats thousands of times. The chain reaction continues until termination occurs. When any two radicals collide and combine, such as two halogen radicals, a carbon and a halogen radical, or two carbon radicals, their unpaired electrons pair up, and the cycle stops. Section 2. Radical addition to alkenes. HBr, 𝑎𝑛𝑡𝑖-Markovnikov addition. When HBr reacts with an alkene in the presence of peroxides, the regioselectivity completely flips from the standard electrophilic addition to 𝑎𝑛𝑡𝑖-Markovnikov addition. Let's see why through its three-step mechanism. Initiation involves two steps. First, light or heat cleaves the weak OO bond of the peroxide initiator, generating alkoxy radicals. Second, this alkoxy radical abstracts a hydrogen from HBr, creating a bromine radical. Propagation begins when the bromine radical attacks the alkene's double bond. It adds to the less substituted carbon, placing the radical on the more substituted carbon. Why? Because this leaves the unpaired electron where it is best stabilized, forming the more stable carbon radical intermediate. In the second propagation step, this carbon radical abstracts a hydrogen from another HBr molecule. This delivers the 𝑎𝑛𝑡𝑖-Markovnikov alkyl bromide product and regenerates the bromine radical to sustain the chain. Termination happens when any remaining radicals collide and couple, bringing the chain to a halt. For instance, two bromine radicals can recombine to form Br2. A bromine radical can couple with the carbon radical intermediate to form a 1,2-dibromoalkane byproduct, or two carbon radicals can dimerize. Furthermore, because the carbon radical intermediate is an sp2 hybridized planar species, reactions involving this intermediate at a chiral center occur from either face with equal probability, producing racemic mixtures. Section 3. Allylic radical substitution. To achieve substitution next to a double bond without undergoing competing addition, we utilize allylic radical substitution, most commonly through allylic bromination using NBS, N-bromosuccinimide. NBS acts as a molecular reservoir, maintaining a constant, low concentration of Br2 to prevent direct addition across the alkene. Initiation begins when a trace amount of Br2 undergoes homolytic cleavage by light or heat, generating highly reactive bromine radicals. In the first propagation step, the bromine radical abstracts a hydrogen from the allylic position. The resulting allylic radical is highly resonance stabilized because the unpaired electron is delocalized across the pi system. In the second propagation step, this allylic radical reacts with the low concentration of Br2, yielding the allylic bromide product and regenerating the bromine radical. Because the allylic radical is resonance stabilized, reaction can occur at either resonance position, frequently producing a mixture of constitutional isomers. The chain reaction stops during termination when any remaining radicals collide and couple, such as two bromine radicals recombining, a bromine radical coupling with the allylic radical, or two allylic radicals dimerizing. As a side note, while we've omitted specific RS and cis trans isomers here for simplicity, you can see on the screen that a wide variety of byproducts can form depending on how these radicals combine. Section 4. Benzylic radical substitution. Just as radical substitution occurs selectively at the allylic position, it can also be cleanly achieved next to a benzene ring at the benzylic position. Because the aromatic ring remains intact throughout the process, this pathway provides an efficient route to functionalize alkyl benzenes. Just like allylic bromination, initiation involves the homolytic cleavage of a halogen molecule, Br2, or low concentration Br2 from NBS, by light or heat, producing the initial halogen radicals. In the first propagation step, the halogen radical abstracts a benzylic hydrogen from the substrate, such as ethylbenzene. The resulting benzylic radical is exceptionally stable, as the unpaired electron is extensively delocalized throughout the aromatic pi system. In the second propagation step, this benzylic radical abstracts a halogen atom from another halogen molecule, delivering the benzylic halide product and regenerating the halogen radical to fuel the cycle. Termination occurs when the active radicals pair up and destroy the radical chain. This includes the recombination of two halogen radicals, the coupling between a halogen radical and the benzylic radical, or the dimerization of two benzylic radicals. Here's a quick preview of radical polymerization, which we'll cover in detail in a future video on polymers. Just like other radical reactions, it follows initiation, propagation, and termination. The key difference is that the propagation step repeats thousands of times to build massive polymer chains. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.